Good day, everyone. Welcome to the first part of our discussion on nuclear chemistry. For this lesson, I will be describing with you the makeup of the nucleus. So this is where nuclear power comes from. Also, I will be describing the criteria for nuclear stability and calculate the mass deficiency in nuclear bonding. So these are the laws of electrical charges. Electrostatic forces, if they have similar charges, they repel. And if particles have opposite charges, they attract each other. So for protons that are residing inside the nucleus, the tendency of them is to repel each other. So the strong nuclear forces attract the protons and neutrons. And the balance between these forces determines whether or not a given nucleus will be stable. So although protons tend to repel each other, there is a contradicting nuclear force that holds them together. So the balance between these forces determines the stability of an atom, of the nucleus of an atom. So two main factors that determine nuclear stability are the following. The neutron to proton ratio. So it has something to do with the number of neutrons and the number of protons inside the nucleus, as well as the total number of nucleons in the nucleus. So these are the factors that determine nuclear stability. The basis of this is the existence of unstable isotopes. So in this plot here of the number of protons versus the number of neutrons, we can see that a 1:1 ratio is represented by this line here, this red line here. But there is a shaded portion here which represents ratio of protons and neutrons. So neutrons and protons that are off to a ratio that is equal to 1. So the straight line represents a 1:1 ratio. So what does this shaded portion indicate? So above 20, atomic number equal to 20, so this one, above that, the number of neutrons always exceed the number of protons. Okay, so element 20 is calcium, and there are a lot of isotopes that would be having a number of neutrons that are greater than the number of protons, but they are stable as well. So lower than atomic number 20, isotopes here are mostly stable. So with greater number of neutrons compared to the number of protons, the stable nuclei are located in the pink band, and this band is known as the belt of stability. And the belt of stability ends with lead, element number 280. So lead is element number 80 with a nucleon number equal to 208. Nucleon number is called mass number as well. Okay? So band of stability. So meaning to say, isotopes occupying this region here are all stable. Isotopes that are below the band of stability or below this 1:1 ratio band or above the band of stability, belt of stability, are unstable ones. So what can we say about the neutron to proton ratio? Stable nuclei have neutrons that are greater than the protons. So as you can see here, starting from element number 20, if the number of neutrons is greater than the number of protons, most likely the isotope is stable. So with Z greater than 20, atomic number greater than 20, neutron to proton ratio gradually increases. Ayun na, no? There. So bismuth, atomic number 83, is the heaviest stable nucleus. Heaviest stable nucleus. So it is somewhere here. Even-numbered elements, even-numbered isotopes, that means to say their atomic numbers are even numbers, are more common than odd. So there are more stable, even-numbered atomic numbered isotopes that are stable as compared to the odd numbered atomic numbered isotopes. So there are 160 isotopes with even number of protons and even number of neutrons. And 110 stable isotopes with odd-even or even-odd combination of protons and neutrons. And there are only 4 odd protons, odd neutron isotopes that are known to be stable. So most of them are radioactive. Those are some criteria that we can consider in order to predict whether a particular isotope is going to be stable or not. So no nucleus higher than lead-208 is stable. So most of the isotopes beyond lead-208, so beyond element number 80, there is that more likeliness of the isotope to become unstable. That's because although the nuclear strong force is about 100 times as strong as the electrostatic repulsion, it operates over only very short distances. When a nucleus reaches a certain size, the strong force is no longer able to hold the nucleus together. So the more particles that are present inside the nucleus, the more it is difficult for the nucleus to handle or to hold them together. And then the instability starts. So unstable nuclei. With the wrong proton to neutron balance, particles undergo radioactive decay. So that is, the isotope will emit radiation, spontaneous radiation. So that's called the decay series. So radioactive nuclei spontaneously decay or undergo nuclear reactions. So when an isotope is unstable, it's going to give off a lot of energy in order to convert it into a more stable isotope. So the degree of unbalance of the proton to neutron ratio determines the type of decay. So radioactive nuclei is referred to as the parent nuclei, and it decays into a daughter nuclei. So the parent nuclei is the starting isotope of an element, and it decays and gives off energy and radioactive particles to form a new element isotope. And this is called the daughter nuclei. So that's the first part of our lesson. I hope you understand why there are isotopes that are unstable and radioactive. So thank you for watching. Well, let's now go to the next lesson.